In this video, we're going to begin discussing conditional probability. What we have been discussing so far is probability that is computed without knowledge of additional information, which is also known as unconditional probability, meaning we know nothing about it, so there's no conditions already placed on it, and everything has the original probability of happening. Well, a probability that is computed with the knowledge of additional information, so we know something else about it, is called conditional probability. Conditional probability is looking at items that we know something about. For example, if you are thinking of going to a restaurant, if you just put restaurants' names in a hat and draw one, that's unconditional probability. But if you know something about what you're looking for, you narrow it down by, say, the type or the price that you want to pay. Those are conditional probabilities because the probability that we go to one restaurant over another has changed based on information that we already know. So let's look at this example. The table represents the marital status of males and females 15 years or older in the United States in 2010. So in 2010, there were 40.2 million males that had never married. This is a contingency table, which we've discussed before. And so when we have a contingency table, remember that we have to find the total of each type of male, female, married, never married, and then we have to find our very total of how many people are we talking about. So never married, there are 74.2 million, because we're talking about in millions here, people that have never been married. There are 124.2 that are married. There are 14.4 that are widowed. There are 23.8 that are divorced, and there are 5.6 that are separated. We have a total of 117.8 males. I've added all of these up. And there are a total of 124.4 females that were surveyed in this particular item. If I add the males with the females, I add all of these, this column should equal this row of 242.2 million people 15 years or older. So find the probability that a randomly selected individual 15 years or older is widowed. So we want the probability of being widowed. Well, if I look at the widowed, here are my widowed. There's a total of 14.4 million people that are widowed, and there are 242.2 million people 15 years or older. I divide this out and I get 0.059. So the probability that a randomly selected individual 15 years old or older is widowed is 0.59, 59 thousandths. Again, the probability that a randomly selected individual 15 years old or older is widowed is 0.059. So now then, suppose that we know the individual is female. What this says is whenever I know that they're female, that means I know that I'm looking at strictly these people right here. I'm not looking at any of the men, and now my totals are now gone because I'm looking at strictly the females. We know that the individual is female, find the probability that a randomly selected individual 15 years old or older is widowed. So when we're talking about widowed now, we're talking about only this part right here out of the total 124.4 million females. So in this case, the probability of being widowed, and then I'm going to draw this line. This line means given, means I know some information. Given they are female is equal to, there were 11.4 million widowed females, and there were a total of 124.4 million females. So you'll notice that my female is the amount that I know. That goes on my denominator. That is my new denominator. And where they intersect, where they both occur, is now my numerator. So I'm going to take 11.4 divided by 124.4, and I get 0.092. So the probability a randomly selected individual, 15 years old or older, is widowed given the individual is female is 0.092. Because we know the individual is female based on information given to us. So when we're looking at this, you'll notice that I put this line here. Again, that line means given. So we're denoting the given by probability of B given A. And the formula for this is the probability of both events occurring, A and B, divided by the probability that only A occurs. Our given portion goes on the denominator. Their intersection goes on the numerator. So let's look at example 2. A survey found that 56% of students live on campus. So I'm just going to go ahead and look at probability that they live on campus is 0.56. I changed the percentage into a decimal. 62% have a campus meal plan. So the probability of a meal plan is 0.62. So let me 62%. Or 42% do both. So this means that they live on campus and have a meal plan. So the probability they live on campus and have a meal plan is the 0.42. While dining in a campus facility open only to students with meal plans, you meet someone interesting. What is the probability that your new acquaintance lives on campus? Now we have to look at some of the information. While dining in a campus facility that is only open to students with meal plans. So what information do we know about this person? We know they have a meal plan. Have meal plan. We want to know if they live on campus. So we want to know the probability that the person lives on campus given, because we know they have a meal plan. So recall, the formula says the probability that both occur divided by the probability of the given, which is the meal plan. So in this case, both of them occurring, they live on campus and have a meal plan, is 0.42. The probability that they have a meal plan is 0.62. Divide these out and you get 0.677. There's a probability of about 0.677 the new acquaintance lives on campus. So I recommend that you begin looking at problems with conditional probability, with givens, and see if you can pick out the given part, see if you can do these calculations, and then let me know if you have any questions.